Hello, calculus fans. Okay, so let's look at a problem involving particle motion, and we'll use this net change theorem that we talked about in the last video. Okay, so we're going to have a 30-meter high balcony, and a rock is thrown upward at the rate of 20 meters per second. We want to find the total distance traveled. This rock is going to go up, and then it's going to fall back down to the ground 30 meters below this balcony. All right, so we know how to come up with a position function. We've done this before. Our acceleration is negative 9.8. So we compute an antiderivative to get the velocity function. The most general antiderivative will be negative 9.8 t plus some arbitrary constant. And now we're going to plug in the initial velocity. We're given that in the problem because this right here is how fast it's going at the beginning. So v of 0 is equal to 20, and so this is going to give us our velocity function. We're going to do one more antiderivative to get us a position function. So same way that we've done this before, we have a position function which is negative 4.9 t squared plus 20t plus d. We have our initial position. That's the 30-meter high balcony. So at t is equal to 0, our position is 30. All right, so we've got our general position function. Now we could answer the question as it's given using just this position function. But what I want to do is show what the net change theorem can tell us. All right, well, let's first figure out how long it takes for the object to fall to the ground. So all we do is we set the position function equal to 0 and solve for t. All right, so we just plug everything into our handy-dandy quadratic formula. We get this messy-looking expression. That cleans up a little bit. The radicand comes out to be a nice whole number, 988. Okay, so let's work out a couple of these two solutions. So our first solution ends up being about negative 1.17. The other one is about 5.2. Now we can throw this one out. It doesn't make any sense to talk about negative time. We're not going to go backwards in time. So really, this is the solution that we want. That's how long it takes for the rock to fall from our 30-foot high balcony. Okay, so it takes about 5.2 seconds for the rock to hit the ground. And I would just like to let g be equal to this number, because I'd like to use this later on, so it'll be convenient to have a notation for it. Right, so to compute the distance traveled, we're going to compute the integral from 0 to g of the absolute value of v of t. I'm using g, by the way, to just indicate ground. That's the time when it hits the ground. And remember that the distance traveled can be calculated using an integral of the speed. Okay, now here's the other piece of information we need. Now we know that we're throwing the rock up, and then eventually it turns around and starts falling. So we need to find out when that happens. When does it reach its apex, the highest point? Well, at the apex, the velocity is 0, so we'll just set our velocity function equal to 0 and solve for t, and we just get 20 over 9.8. All right, so we know now that the velocity is positive when t is between 0 and 20 over 9.8, and then the velocity is negative after that, after 20 over 9.8, at least until it hits the ground, and then we had determined that it hits the ground at this time here, negative 20 minus root 988 over negative 9.8. Okay, so I'm going to pick a new time now, a new letter for this time, 20 over 9.8. That's going to be A. So A represents the time and when the rock reaches its apex, and G represents the time when the rock hits the ground. A for apex, G for ground. These are times at which they occur. Okay, so now we can calculate the distance traveled. Now we've discussed this, that the distance is equal to the integral from 0 to g of the absolute value of v of t. Now we're going to break this up into two integrals. The integral from 0 to a and the integral from a to g. The reason we're breaking that up is because that's the time at which the rock stops going up and starts going back down. See, we have to get rid of this absolute value in the integral before we can proceed, and breaking it up at this point will help us in that regard. And the reason it helps us is because in this initial segment, the velocity is positive, and in the last segment, the velocity is negative. So that way, when we remove the absolute value, we have to put in a negative sign in the second one, and on the first one, we can just remove the absolute value without any other change. Okay, so now we can put the v of t in there. Notice that in the second integral, that minus sign has to get distributed to each part. And now we can just use the evaluation theorem to evaluate these integrals. Okay, now if you go back, we have values for a and g. We can plug these in and use the evaluation theorem. I went ahead and did all the dirty work for you. And I got just under 71 meters. And that's how far the rock travels, going up and then falling and coming back down and hitting the ground. So again, this first integral here represents the distance traveled by the rock until it reaches its apex. The second integral represents the distance traveled by the rock between the apex and the ground. I definitely think this is not the most efficient way of determining the answer to this question, but it does illustrate the interpretation of the integral of the absolute value of v of t as giving you a distance traveled. You might try to think about how could you calculate this in a much more efficient manner. Okay, that's all for now.